One element that we're going to see in 2D particle equilibrium and then later again in 2D rigid body equilibrium are linear springs. Now we've seen linear springs before when you took your Newtonian physics class, and we know that linear springs are going to behave according to Hooke's law, which we're going to use in two different ways here. So what does Hooke's law tell us? It tells us that the force produced in the spring is going to be proportional to the deformation in the spring by some constant k, which we're going to be calling the spring constant. Now we can have two expressions here for calculating the force in the spring, which I'm going to designate as F sub k. So it is just a force, and just the k subscript is going to remind us that that force is being produced by a spring, which has this special relationship between the force in it and its displacement. So we can use the first equation here. It's k times L prime minus L naught, or we can say that the force in the spring is k times delta. Now all delta is the change in length of the spring, which I'm defining here as this L prime minus L naught. So this is an additional equation that we're going to need to remember and use anytime we know we have a spring in our system. Now we have to pay attention here to how am I defining delta? How am I defining the change in length of the spring? Well, I'm assuming here that the spring is in tension with this equation. I'm saying it's L prime, which is the current length of the spring, or the length of the spring when our system is in equilibrium, minus L naught. So L naught is going to be the unstretched length of the spring. So if the spring were just resting on the table with nothing else acting on it, L naught is how long the spring would be. L prime is a measurement of, in its current situation in equilibrium, if we measured the spring end to end, how long is it? So it's going to be basically the new length minus the original length. So by having it in the form of L prime minus L naught, we're automatically assuming tension. Because if it's longer than it is when it's unstretched, if L prime is greater than L naught, then that delta is going to be positive, and thus F sub k will be positive, since the spring constant must be positive. If the spring is in compression, meaning that L prime is smaller than its original length, so L prime minus L naught is negative, well, we have k times a negative delta gives us a negative F sub k. So as long as we are using this formula, we are going to be assuming tension, meaning that whenever we draw the force due to a spring acting on our object, we want the arrow pointing away from our object, denoting that our assumption is that the spring is pulling on our object. The spring is thus in tension. And like other times where we make an assumption about tension or compression, if our assumption is wrong, that's okay, the negative sign will tell us that. But as long as we were consistent in our use or our assumption of the tension or compression of the spring, everywhere we used it, that negative sign is just going to pass through all of the equations, and it's automatically going to work out for us. Now, how do we include this force, this spring force, when we're drawing our free body diagram? At the free body diagram step, all the object knows is it's attached to something that's producing a force on it. So whether that force is due to a cable, which does not adhere to Hooke's law, the force in it is not proportional to its deformation, that cable is still just applying a force on our object. Same is going to be true for a spring. The spring is applying that push or pull on our object, and that's all the object knows. The object does not need to know in the free body diagram that it's a spring. So where do we include the information that there is a spring in our system? Not in the free body diagram, not even in the equilibrium equations. It's just going to be another force in those equations. Where we include Hooke's law and this spring relationship is going to be in our equation step, and typically just after we write our equilibrium equations, we're going to have this extra piece of information here that not only is there a force acting on our body, but for the spring force, we know that this relationship, that the force in the spring is proportional to the deformation, is also going to be true. So it's typically going to add another equation for every spring involved in our system.